It's my pleasure to welcome Noah Tuchow, who is a graduate student at Penn State working on a dual title PhD in astronomy and astrophysics and also astrobiology. And Noah's research focuses on the long-term habitability of exoplanets, particularly as it relates to stellar activity. So Noah, I will turn it over to you, and thank you so much for coming and talking to us today.
Okay, let me share my screen. Can everyone see this full screen?
Looks good on my end.
Okay, so I'm Noah Tuchow from Penn State, and I work with Professor Jason Wright, and I'll be presenting my research on potential habitability as a stellar property, assessing the habitable histories of stellar systems. So the motivating question for my research is, what type of stars are the best targets for a search for biosignatures? So I'm going to list a bunch of different types of stars. Some of these will be good targets, some of these will be not so good targets. And I want you just to, while I'm listing these stars, think whether or not this would be a good target star. So would we want to look around young flaring M dwarfs? Or blue hypergiants? What about solar analogs? Or white dwarfs? What about older K stars? What about red giants? What about brown dwarfs? So of these types of stars which I listed, you probably have a qualitative understanding about which of these would actually be a good place to search for biosignatures. So typically the scientific consensus is that we typically prefer to search around sun-like FGK stars. So we also want to look around older stars, and this is typically because of the timescales it took for complex life to evolve on Earth. It took around 2 gigayears for photosynthesis to develop on Earth, and even longer for oxygen to become a detectable biosignature in the Earth's atmosphere. And typically we don't want to search around more massive stars or giants, neutron stars, or white dwarfs due to their potential obstacles for habitability. So we have all these intuitions, and we want to find a way to quantify and formalize this intuition. So my talk will be organized into 3 different parts. First, I'll talk about the time dimension of habitability. Then I'll talk about how we go from habitability to biosignatures. And then I'll talk about the application to direct imaging missions. So let's first talk about the time dimension of habitability, or what I call habitable histories of planets. So most astronomers are familiar with the concept of the habitable zone. This is the range of distances from a star where an Earth-like planet could support liquid water on its surface. The classical habitable zone typically assumes CO2 and H2O are the dominant greenhouse gases, but there's many different formulations of the habitable zone. Some introduce different greenhouse gases, such as methane, or different treatments of atmospheric phenomenon. And so astronomers can use the habitable zone, and they can calculate the distances of the habitable zone using only the luminosity and effective temperatures of the host stars. So this makes the habitable zone a very powerful tool for astronomers, just because they don't need that many observations to actually measure it. So the habitable zone only gives a snapshot in time. It doesn't actually so the habitable zone only gives a snapshot in time. It doesn't really tell you the history of the planet, but it just tells you if it currently lies at a habitable distance from the star, given which is dictated by the model that generated the habitable zone. So we typically refer to this habitable zone as the instantaneous habitable zone, or like the current day habitable zone is the instantaneous habitable zone. And so a planet that you find in the current day habitable zone could have stayed there for billions of years, or it could have just entered it. So stars evolve and change over time, and as they evolve and change, so too do their habitable zones. So this plot over here, can you see my mouse? This plot over here is showing the habitable zone boundaries for a solar analog evolving over time. And you can see that as the star evolves, the habitable zone gradually moves outwards, distances on the x-axis and ages on the y-axis. And I guess we'll ignore those regions for now, but there's a continuously habitable region which stays habitable for the duration of the star's evolution, and then there's a region which enters the habitable zone as the star evolves. So we can come up, like, based off the star's evolution and based off the evolution of the habitable zone, we can come up with several classes of planets. They're continuously habitable planets, which have stayed habitable since their formation, or stayed within the habitable zone inner and outer boundaries. Whether or not they're actually habitable remains a question. And then there's belatedly habitable planets, which is what we're calling planets that enter the habitable zone from outside as the star evolves. So to be clear, we're not considering the effects of migration, we're considering the effects of the habitable zone itself moving. So of these belatedly habitable planets, there are actually two subclasses. There's inner belatedly habitable planets, which lie in what we call the inner belatedly habitable zone, which are planets that originate from inside the inner edge of the habitable zone and enter it maybe as the host star dims. And then there's outer belatedly habitable zone planets, which are planets that enter the habitable zone from outside the outer edge. So as the star potentially increases in luminosity. And sometimes these outer belatedly habitable planets have been referred to as cold starts, such as in casting 93. But this term has the potential for confusion, since there's also the use of the term cold starts in the context of giant planet formation, which doesn't really have anything to do with these class of planets. So the relative sizes of these regions of the habitable zone depend on the stellar age and the stellar mass, and they evolve in time. So over here, we can see the habitable zone evolution for two stars of different masses. We have a 0.5 solar mass star and a 1 solar mass solar analog. And these black lines over here represent the inner and outer habitable zone boundaries. We're considering habitability to start at 10 to the 7 years, like 10 million years, which is roughly the time scale of the protoplanetary disk. That may be a bit early to habitability to start, but for these figures, we're using that. And so we can see that like the region which stays continuously habitable is given by these green regions, which gradually shrinks over time. In this 0.5 solar mass star, only a very, very tiny portion of the habitable zone remains habitable, remains continuously habitable for a long duration. And then these orange and blue regions represent the inner and outer belatedly habitable zones. So planets falling at this distance will have previously been too hot, but will have previously been interior to the habitable zone. But as the M star dimmed, they gradually entered the habitable zone. Whereas these stars, whereas these planets used to be outside of the habitable zone, outside the outer edge, and as the star increased in luminosity, they gradually entered it. So for a 1 solar mass star, you can see that the continuously habitable region is much larger than that for a 0.5 solar mass star. And for most ages, including like the current age of the sun, it makes up a substantial portion of the current day habitable zone. However, the fraction of planets that belong to the outer belatedly habitable zone, these planets that enter from outside the outer edge, gradually increase in time. And eventually, like in the late evolution of the star, like in like the subgiant branch, they'll reach a point where all the planets in the habitable zone will belong to that class of planets that have entered it from outside. So why is it considered? So why is it important to consider the belatedly habitable zone, or what I'm calling BHC? I'm using that as abbreviation. So many, if not the majority, of planets that we find in the habitable zone will belong to this class of belatedly habitable planets. So we would like to know what portion of habitable zone planets are in the belatedly habitable zone. This depends on a bunch of factors, including when we consider habitability to start. And this is a pretty complicated issue, which doesn't really have consensus, but habitability, but the onset of habitability would depend on the onset of plate tectonics and also the delivery of volatiles to otherwise habitable exoplanets. So in these two plots over here, I'm plotting the fraction of planets in the belatedly habitable zone as a function of stellar mass and stellar age. So let's first look at this plot where I'm considering habitability to start at 10 million years. So over here we can see that the fraction of planets in the bladely habitable zone does depend pretty strongly on the mass and the age of the host star. We can see that some lower mass stars, like the cutoff is around 0.5 solar masses, some lower mass stars have almost all of their planets in the bladely habitable zone, which is not surprising because M dwarfs spend a long duration dimming before they settle onto the main sequence, or even in the early main sequence, they still dim for a little bit. And then for higher mass stars, you also get a very, very large fraction of bladely habitable planets just because they don't live for that long. So we can see that these white lines over here represent the zero age main sequence and the terminal age main sequence respectively. So for the sun, which is represented by this dot, we can see that the sun is kind of in the middle, where it's roughly around 50% of habitable planets. And so if we actually take an average of like a realistic planet distribution and a realistic sample of host stars, we would get that roughly 75% of planets would fall in the bladely habitable zone. Whereas if we consider habitability will start at 100 million years, then we would only expect the fraction of planets in the bladely habitable zone to be 32%, which is still a very large fraction of habitable planets. So even if only 32% of habitable planets fall in this region of the habitable zone, we still want to characterize whether or not 30% of planets could be habitable. 30% of habitable zone planets could be habitable. And so also these different starting scenarios can also somewhat represent different scenarios for the delivery of volatiles. So 10 million years starting time for habitability would be comparable to if a planet obtained most of its volatiles from the protoplanetary disk, whereas a 100 million years starting time for habitability would represent if a planet obtained most of its volatiles from impacts that are late Vanir accretion. So the fraction of bladely habitable planets depends on when habitability is considered to start, as well as the mass and the age of the host star. And one should not assume that these bladely habitable planets are habitable just because they fall in the current day habitable zone. So we would like to know whether or not bladely habitable planets can actually be habitable. So there's a lot of potential obstacles to the habitability of these planets. For inner bladely habitable planets, entering from interior to the inner edge of the habitable zone, so many of these planets may be depleted in volatiles. They may be desiccated due to extreme UV fluxes and just like high luminosity of the star into the habitable zone. And this is particularly an issue for low mass stars, that spend hundreds of millions of years contracting and dimming before they settle on the main sequence. However, recent studies show that it's possible to attain volatiles during an early magma ocean phase. So if a planet manages to sustain a magma ocean phase for a substantial period of time, they could potentially keep the reservoir of volatiles, even if the upper atmosphere would be desiccated. So outer habitable zone, so outer bladely habitable zone planets have their own obstacles to habitability. These planets would be somewhat similar to the snowball Earth stage in Earth's early evolution, which means that they would have high ice albedo and they'd be very difficult to melt. And the fluxes required to thaw these planets may be high enough that it may directly lead to a runaway greenhouse effect. And also these planets, since they're covered in ice, they may have difficulty outgassing a thick enough atmosphere in order to keep them warm enough. So there's several open questions when it comes to this class of bladely habitable planets. So the obvious question is, can these bladely habitable zone planets be considered habitable? And then this has an added question about when do we actually consider habitability to start? What are the timescales for the onset of plate tectonics and the volatiles? And how does the ambiguity of the habitability of bladely habitable zone planets affect the search strategies for future missions to image Earth-sized habitable zone planets. And then we'd also want to know whether or not future missions would be able to empirically test the habitability of bladely habitable zone planets. So now I'm going to talk about going essentially from habitability to biosignatures and searches for biosignatures. So just knowing if a planet is bladely habitable or continuously habitable doesn't necessarily tell us how long it's been in the habitable zone. To search for biosignatures, we would like to find planets that have been in the habitable zone for an extended period of time. Life on Earth took around 2 billion years to produce oxygen as a biosignature, and it took around 4 billion years for oxygen levels to become high enough to be detectable in the Earth's atmosphere. So we've come up with this quantity which we call the habitable duration of a planet. This is the time spent in the habitable zone as a function of the distance from the host star. So this plot is for a solar analog, and we can see that a distance here is on the a solar analog of comparable age to the sun, so like 4.6 gigayears. You can see that the distance from the host star is on the x-axis, and the duration the planet spends in the habitable zone is on the y-axis, and this is based solely on the evolution of the habitable zone over time. So these two dotted lines over here represent the habitable zone at when time is so these dotted lines over here represent the habitable zone at the zero age main sequence, and these dotted lines over here represent the habitable zone at the current day. And this curve shows the duration spent in the habitable zone as a function of distance from the host star. The red regions are currently outside of the habitable zone, and in some formulations of this, we actually set them to 0 because they're not particularly useful in a current day search for biosignatures. So we can see that there's this large plateau region which has stayed at the same duration of habitability for the entire duration of which has stayed habitable for the entire duration of the star's existence. And then there's this region over here which has entered the habitable zone from outside. These are the outer bladely habitable zone planets, which were sometimes formally known as cold start planets. So for every star, we can essentially, so for every star, as long as we know its evolutionary history, we can develop a habitable duration curve. And then we can see how this habitable duration curve evolves in time. So this is for a solar model, and we can see that as the curve evolves, the inner edge of the habitable zone gradually recedes, and more planets enter from outside the outer edge because the sun is gradually becoming more luminous in time. And so these different contours represent different ages, and you can see that the habitable duration curve is gradually getting taller and skinnier in the plateau region, but larger in the sloping region that represents the outer bladely habitable planets. And so looking at this curve, we had the idea that the area under this curve might be a useful quantity in determining long-term habitability. So essentially, without knowing whether or not a planet hosts, without knowing whether a star hosts planets, using the integral of this habitable duration curve would tell you essentially its potential for supporting long-term habitability. So we've come up with a general form for metrics for how likely a star is to host general form of metrics for how likely a star is to host biosignatures. So this is quantity B, which is the integral of two functions, h and gamma, which I'm going to describe. So gamma is the planetary distribution function. It's distribution of planets inside major axis and radius. Whereas h is the probability of biosignature emergence as a function of distance and time. So neither of these functions are particularly well characterized, but we have good. So h and gamma lack empirical constraints, but we have pretty good models and hypotheses to constrain them. So for gamma, one can use any realistic distribution for planets in the habitable zone, such as an extrapolated power law. And here we'll listen to contrasting forms of gamma. So a gamma that's uniform in sine major axis, and a gamma that's uniform in log sine major axis. and the function H, which is the probability of biosignature emergence, can incorporate how long planets maintain their habitability throughout the evolution of their host stars in luminosity and temperature. So what are some potential options we could use for H? So one could assume that all planets in the current day instantaneous habitable zone have the same chance of hosting biosignatures. This is a somewhat naive assumption, but it's often implicitly assumed just by assuming that all planets in the habitable zone are habitable. One could assume that the probability of biosignatures is constant if a given duration has been spent in the habitable zone. One could also assume that the probability of hosting biosignatures is proportional to the time spent in the continuously habitable zone. Or one could assume that the probability of hosting biosignatures is proportional to the time spent in the habitable zone, which also includes these blatantly habitable planets. So we want to quantify these assumptions, and we've developed a flexible framework to assess how likely stars are to host biosignatures on their planets. Those examples that I gave for the quantities H and gamma were suggestions, but realistically anyone can use this framework with their own formulations of H and gamma. And so we think that this framework could potentially be useful for prioritizing target stars for future missions and interpreting positive results. So we will investigate how different sets of assumptions affect which stellar populations are preferred by these metrics. So here we talk about how different formulations favor different types of stars. So in this plot over here, metrics are calculated for a grid of stellar models in mass on the x-axis and age on the y-axis. And the rows are called, so the rows over here are assumptions about the probability of biosignature emergence, and columns are assumptions about gamma. So over here, this is saying that all planets in the habitable zone, well, this one is saying that the duration spent in the habitable zone, including these blatantly habitable planets, is what affects the probability of biosignature emergence, whereas this one says the probability of biosignature emergence only depends on the habitable duration of the continuously habitable zone planets, whereas this one is just assuming that all planets in the habitable zone are equally likely to host biosignatures, which is potentially not a good assumption, but it gives a good contrasting metric from the more physically motivated ones. And then over here we have the planetary distribution function is uniform in semi-major axis, and the planetary distribution function is uniform in log semi-major axis. So one can observe that these different assumptions lead to very different stellar populations being preferred. The red regions over here have higher values for the metrics than the blue regions in those color maps. So pay attention to the right-hand panels, which have a more physical assumption for the distribution of planets, the uniform and log A distribution. This represents so if we look at the upper two panels, which have a habitable duration dependent probability of biosignature emergence, we can see that this replicates our intuition that older low mass stars are the best candidates for biosignature searches. If one only assumes that the planet is in the habitable zone, that's a good candidate, then obviously over here we see that almost all candidates are equally likely to host biosignatures, so they have a pretty uniform spread of the metric. Whereas for a somewhat non-physical assumption about the planetary distribution function, we can see that vastly different populations of planets are preferred. So if all planets in the habitable zone are considered equally habitable, then this metric would consider higher mass stars and older stars, which are more luminous, to be the best candidates, which is not actually a very good metric to use because we know that those stars have large obstacles to habitability. So the bottom line of this plot is that considering the duration spent in the habitable zone has a major effect on which stars are preferred. So let's talk about how these metrics can potentially be applied to direct imaging missions. So our metrics would be potentially able to rank stars based on their potential to host planets with long-term habitability, even without knowing that a system hosts planets itself, as long as we know the planetary distribution function. So future missions aim to obtain the spectra for Earth-sized habitable zone exoplanets. And there's multiple methods how to do this. There's transit spectroscopy, but what I'm going to focus on is primarily direct imaging missions. So future missions want to determine the atmospheric compositions of Earth-like planets and search for biosignatures. And we propose biometrics could be a useful tool for target prioritization. So I know a lot of people at Goddard do work on direct imaging, so I won't go into too much detail about this, but I'll give a brief review about direct imaging for those of you who aren't familiar. So direct imaging is directly getting the light and the spectra of Earth-like planets around stars, or well, it could be any planets around stars. We're particularly interested in the case of Earth-like planets, but direct imaging is very difficult with the current technology because of primarily that stars are bright and planets are really dim. So we need a way to mask the starlight with a sophisticated chronograph. And planets are dim, so direct imaging as a detection technique is currently sensitive to larger and younger soft luminous planets, and also planets that are farther away from the host star. Additionally, there's additional obstacles to direct imaging caused by exozodiacal light in planetary systems, which is dust that scatters light and adds a background light to planetary system, where planetary systems make it harder to image dim Earth-like exoplanets. And so imaging smaller planets around stars may require long exposure times in order to actually obtain their spectra. So future direct imaging, so current direct imaging is limited to far out giant planets, but future missions want to extend the capability to include Earth-sized planets in the habitable zones of their host stars. So this would require a very sophisticated chronograph and telescope. So in the 2020 decadal survey, there are two proposed exoplanet direct imaging mission concepts that have been submitted. So there's the HabEx mission concept, which has a 52-meter external star shade and a 4-meter telescope diameter. It also has an additional internal chronograph and a UV spectrograph. Then there's the LUVOIR mission concept, which has two potential light detectors. There's the 15-meter LUVOIR-A and the 8-meter LUVOIR-B. And LUVOIR has a wide wavelength coverage covering the UV, optical, and infrared bands. And LUVOIR uses a sophisticated internal chronograph. So these missions aim to image Earth-like planets. So these missions aim to image Earth-like planets in the habitable zone. But even with the sophisticated technology of these missions, they're still limited to nearby bright stars. So these missions will need to select target stars to observe the maximum yield of Earth-like planets. And we argue that target selections will also consider stellar evolution and how long planets stay habitable. And we suggest that our metrics could be used for target prioritization. So we would like to rank stars according to our metrics, but we want to know how precisely we can actually determine the value of the metrics for a given star. So we find that the uncertainty in our metrics come from two sources. There are systematic uncertainties from fitting stellar models to observations, then there are uncertainties in the models themselves. So we'll give a brief overview about what we're doing in an ongoing sensitivity analysis of these metrics. So let's talk about model uncertainties first. So stellar models give the evolutionary tracks of a host star, and are used to calculate the metrics that we use. However, models often contain uncertain physics, and different models may conflict with each other. There are several open problems we'll talk about. There's the faint young sun problem, the warm early Mars problem, and the solar abundance problem. I believe I have slides dedicated to each of these. Okay, so let's talk about the solar abundance problem, or the solar modeling problem. So using the 1988 Griffiths-Fall surface abundances, one could evolve a one solar mass star and have it result in surface properties and interior structure that match those of the sun. However, with newer measurements from Aspendel, the solar models no longer match these sun's observed properties as well, which is surprising because we have better measurements of the sun's photospheric chemical abundances, but those measurements don't fit the interior models as well. And this seems like an apparent disagreement between stellar modeling results and helioseismology. This is most apparent in the sound speed profile and density. So over here in the black curve, we can see the deviation in the sound speed profile from that of helioseismology as a function of stellar radius. And we can see that for the 1998 model, it was pretty small, but for the 2009 model, it is increasing substantially, despite getting better spectral resolution and more sophisticated models. And similarly, with the density profile, there's larger discrepancies in density with the newer models than with the older 1998 models. So there's several potential solutions to this solar abundance problem. One could be that the newer aspect abundances are just incorrect. And so different models differ about which set of solar abundances they use. Some models use the 2009 newer abundances, despite their disagreement with helioseismological results. Some models cling to the older 1998 abundances, and others use different sets of abundances, potentially the Ashton abundances are modified with different amounts of neon or other elements. There's also the question about whether or not our stellar opacities could be wrong, so the element opacities in stars. So in a laboratory setting, we observed that iron opacity is higher than what's typically used in stellar models. So there's a question about whether or not other opacities are actually correct based on theoretical models. And so different models vary in the opacities and also equations of state which they use. There's also the question about a treatment convection. So most stellar structure and evolution models are 1D and use 1D mixing length theory for convection. But there's suggestions that 1D mixing length theory may be inadequate to match the 3D atmospheric results. So it's also unclear how to handle convective overshoot, or whether or not convective overshoot even results in physically meaningful results. So also between stellar models, there's different treatment of rotation. And also they have different atmospheric boundary conditions, so surface conditions at the edge of those stars, at the edge of the star's photosphere. And then there's also the faint young sun problem, which is kind of a combination of a disagreement disagreement between stellar models and geophysical models. So early in the Earth's evolution stuff, Earth is known to have hosted a liquid water around 4 billion years ago, but current models suggest that the sun would have only had around 70% of its current luminosity. This problem is potentially resolved by having a thicker atmosphere of greenhouse gases on the early Earth. However, there's also the warm early Mars problem, which models say that Mars shouldn't have been warm enough to. So models say that Mars should not have ever been warm enough in the past to support liquid water, but we have evidence to. But we have strong evidence to support that it did have liquid water on its surface in the past. So how does one go about determining the model uncertainties? There are hundreds of model parameters to vary, and it's not feasible for a sensitivity analysis to vary each one individually. So instead, we're going to use the methodology of Tuchow et al. 2020 and compare the results from 4 well-established stellar models with different input physics. These include the Yale rotating evolution code, the MESA isochrones and stellar tracks, NIST, the Dartmouth stellar evolution program, and the Gershing stellar evolution code. So for each of these model grids that have been pre-calculated, we will calculate our metrics for each star and see the differences between models. So these model grids are calculated in terms of the mass of the host star and this quantity called EEP. Now EEP represents the equivalent evolutionary phase of a host star. So around 200 is the zero age main sequence, and around 450 is the end of the main sequence, and around 600 is the end of the subgiant branch. And so stars with the same EEP will have different ages. So these different panels over here represent the different models of missed the Yale rotating evolution code, Gaussian, Dartmouth. And this color bar over here represents the actual value of our metrics in solar units. This is actually a particular metric that we're using, which has a probability biosignature emergence is linear in the Habitable duration, including bladely habitable planets, and the planetary distribution function is uniform in log square major axis. So one can see that, and also over here we have contours for the age of the host star in billions of years, and we've currently cut off this at around 10 billion years to make it to make the color scale realistic for field stars that one might expect, which are not likely to be over 10 billion years old. So one can see that between the models, the age contours don't agree, and also there's some disagreement between the values of the metrics for the different models. So one can see that in each of these plots, the stars with the highest values for these metrics are potentially lower mass stars that are potentially older, lower mass stars. But lower mass stars tend to have a disagreement about the age, which is larger than those for higher mass stars. So one can see in this plot, we're essentially plotting the largest difference between these different panels as a function of mass and evolutionary phase. And this is also in the same units of a solar units of this metric. And one can see that there's a large disagreement for low mass stars, and those stars with the highest values for these metrics also tend to have the highest disagreements. So, and this disagreement is primarily due to disagreement between the models about how quickly stars evolve on the early main sequence. And then there's also another disagreement over here around the subgiant branch, which is these models also disagree about how quickly stars evolve on the subgiant branch, which some models have them evolving much more quickly than others. So now let's talk about getting systematic uncertainties for our metrics. So we obtain masses, ages, and also values of metrics for different stars by fitting stellar models to observables. So, and we would like to know what precision we can determine these metrics for a typical star, ignoring model uncertainties. Just using a given model, how precisely can we determine our metrics? And how does improving measurement precision of certain properties affect the precision of our metrics? So if we can attain better measurements in a certain property, how will that affect the precision of our metrics? So we'll start with a model of a solar analog observed from 50 parsecs away, and we'll fit stellar models to observations of effective temperature, Fe on H, log surface gravity, Gaia band magnitudes, and parallax. And so we use a standard set of a normal uncertainties for each parameter, which these uncertainties in each parameter would be potentially good measurements that are close to the state of the art today. And we run MCMC chains for each star to determine the uncertainty and derived parameters such as stellar masses, ages, and also the metrics that we're calculating. So we scale the uncertainty in each observable and determine how it affects the uncertainty in derived parameters. So these plots over here show how scaling the uncertainty in observed properties relates to uncertainty in derived properties. So in each of these plots, we have the scale of the uncertainties and the percent uncertainty in all of these different properties. So these are three different metrics. This one depends on time spent in the continuously habitable zone. This one depends on time spent in the habitable zone in general, including these bladely habitable planets. This one depends only on if a star has spent only if a planet has spent 2 gigayears or more in the habitable zone. And then there's also mass and age plot on these. So, and each of these represent different quantities. So this total uncertainty one is scaling the uncertainty in all of the all of the observable properties, whereas this one is scaling the uncertainty in effective temperature, scaling the uncertainty in metallicity, and scaling the uncertainty in surface gravity. And so we allow the uncertainty to go down to potentially unrealistic levels just to see what effect it would have on the percent uncertainty in these derived properties. So one can see that increasing precision in all observables has an obvious effect on metric precision. It's relatively linear in log space. Over here, you can see, yeah. And we find that metrics are more sensitive to certain properties such as effective temperature. So increasing the precision in effective temperature has a much stronger effect on these derived properties than some of these other properties, such as FV on H doesn't typically do a better job of constraining the star if uncertainty is a given close to the current day levels. And log G is somewhere in the middle. It can help you constrain it, but doesn't give a dramatic increase in precision. So we also want to know how exactly do the model uncertainties and systematic uncertainties compare to each other. So we compared values for metrics for different Stirling models, and also compare the uncertainties to which they can be determined with. So we simulate 3 stars at similar evolutionary phases, and we know the true values for their properties. So these are a 0.7 solar mass star, a 1 solar mass star, and a larger 1.25 solar mass star. And so our intuition tells us that the lower mass star should be the best target for biosignature searches, and that the higher mass star should not be a very good target. But we want to see how our metrics actually recover these values and whether or not they can recover them accurately at all. So these are the true values for metrics in solar units. So for the 1 solar mass star, it's obviously very, very close to 1, because it's a very, very close model to the sun. So we determined how well each of the 4 different stellar models can recover the true values. So each of these columns over here represents different stellar models. And these solid markers over here represent the recovered values for the metrics given by isochrone fitting. And one can see that for the that from isochrone fitting, one can somewhat constrain the 1 and 1.25 solar mass star and get values that are pretty close to the true values. For some solar models, they actually directly match the true values, while other ones, they're close enough to be unambiguously ranked. While for the lower mass star, there's much more variation between both the model and also there's much larger systematic uncertainties. So these unfilled markers over here represent the effects of adding 10% model independent age constraint, which would be very difficult to obtain. You could potentially obtain a 10% age constraint via gyrochronology, but that requires a precise rotational period for stars to be known. But it's pretty difficult to get that. But if you can get that, then you can get a much better a model agreement. You can see that adding the 10% constraint immediately makes all of the models much more consistent with each other, and makes the ranking of these target stars much less ambiguous. So particularly for the case of low mass stars, independent age constraints are recommended in order to rank them. But that may not, that may not often be a feasible option with the current amount of stellar periods that have been measured. So our major findings from this research are that our framework allows models for biosignature emergence to be quantitatively connected to targetless prioritization. So different assumptions about biosignature emergence and the distribution of rocky planets affect what population of stars are preferred in the search for biosignature. And stellar age appears to be the most important factor in predicting which stars have the highest chance of hosting planets with biosignatures. Obtaining model-independent age constraints is difficult, but they're especially important for low-mass stars. So what are the next steps in this research? So bladely habitable planets are a rich area for future research, and they make up a large fraction of planets in the habitable zone, but their habitability remains ambiguous. So we plan to model bladely habitable planets and determine what observable features one would expect to observe in the atmospheres, and also whether or not they're habitable. And we want to determine the statistical power to which future missions will be able to empirically test their habitability. And we also want to rank direct imaging target stars in terms of our metrics. So this is non-trivial because a lot of target stars don't have well-characterized masses and ages. So this would require us to for the entire catalog of direct imaging target stars, determine the masses of ages of these stars and also their evolutionary tracks, and compute these metrics. So with that, I'll leave off with questions. Does anyone have any questions about this?
Well, first, I want to thank you for that great talk, Noah. Really interesting work. So yeah, if anyone has any questions for Noah, please feel free to raise your hand, or you can post them in chat and I can read them back to Noah. We have time for a few. While folks are thinking of their questions. Oh, sure. While folks are thinking of their questions, I wanted to kick off. So going kind of back to the, it really came up to me when you were showing that figure of the habitability as a function of the semi-major axis there, like slide 9.
Slide 9.
Yeah, that was a really cool figure, first off. But I was just curious if you could talk about if you've done any work in this, or if you're planning on doing any work on planetary migration and how that could affect these, especially as a function of time.
So I haven't actually done much work in planetary migration, but the same obstacles to habitability will likely be present during planetary migration, although they would happen on different timescales because the migration timescale is typically much shorter than the stellar evolution timescale. Although I guess you can have long-term migration timescales also. But so this plot primarily concerns planets that stay stationary and the stars' habitable zone moving inwards or outwards. So I'm not sure exactly. Does that answer your question? Or?
Yeah, sure. I was just curious if you had any thoughts on it. Very cool.
Yeah, I think it's very interesting to address planetary migration. We haven't really done it yet in this research, but I guess there could be a subclass of bladely habitable planets which are bladely habitable because they've migrated into the habitable zone as opposed to the habitable zone moving to them. Yeah.
Right. Cool. So does anyone else have any questions for Noah? I think I see. Vlad, did you unmute? Or Robbie? It looks like Robbie. We'll have Robbie go first, and then we'll go to you, Vlad.
Okay. Yeah. So that first off, this is a really great talk. But one thing you had mentioned was volatile delivery.
Oh yeah.
And
that slide.
Yeah, I was curious how that might change based on whether or not there's an outer gas giant that may like cut off delivery of material from the outer disk.
Yeah, we've only done a really cursory analysis of volatile delivery. Just essentially, we know that volatile delivery affects the time in which planets become habitable, but we haven't really done a full study into exactly what determines the onset of habitability. So definitely the architecture of the system will determine how quickly or like what mechanism dominates like the volatile delivery mechanisms and other timescales involved with that. So yeah, the presence of like a nearby gas giant or the lack of a nearby gas giant could eventually affect the inventory of volatiles and the timescales when they arrive.
Okay.
But for here, we just consider time habitability starting at this fixed time versus time habitability starting at this other fixed time, and kind of have like a contrasting, showing that essentially what this shows is that regardless of like the extremes of like scenarios of volatile delivery, you'll still have a large fraction of bladely habitable planets.
All right, and Vlad, do you want to go ahead and ask your question?
Yeah, hello. Yeah, so I have a question regarding the slide 9, please.
Slide 9, let me go back to that one.
Yeah. So yeah, I understand that the size of the habitable zone, the inner and outer region, is proportional to square root of the stellar luminosity, right? So the so therefore those distances should go as a square root of of luminosity, and according to the Hayashi track, so the luminosity should go down and then should go up, right? So and I don't understand how do you have those the peak at about 200,000 years in one solar mass star and don't have any peaks for half a solar mass star.
So this peak is kind of due to like the unique like there's like certain wriggles in the evolutionary track which the higher mass stars have, which M dwarfs don't have. So like the like when settling onto, I think this would still count as the main sequence. So when settling onto the main sequence for a solar mass star, you have kind of like the star gradually decreases in luminosity. Hydrogen ignites, it gradually gets a little bit more increase and then stabilizes, and so it decreases a little bit. So that's what that little bump is.
Yeah,
but like the zero age main sequence starts around over here.
Yeah, so for the for the M dwarf star, so you the luminosity goes down, so therefore this distance also goes down, then stabilizes.
Yeah.
Okay. Thank you.
And so these don't have the same scale for the so the scale on the y-axis is different from these. So like it does scale inversely with like the luminosity of like it just does scale as the square root of the luminosity, but they have different scales over here. So the M dwarf does have a much narrower habitable zone, and the solar mass star does have a much wider habitable zone than the M dwarf. And you can kind of see that when the a solar mass star reaches a subgiant branch, its habitable zone gets much wider because it gets more luminous.
Thanks.
Great. Does anyone else have any other questions for Noah? All right. Well, if not, then Noah, thanks again for coming out and talking with us today. It was a really great talk, and I believe Noah is on the postdoc market soon. So if anyone has any suggestions or advice for him, feel free to reach out to him, or you can reach out to me if you have need Noah's email address. But thanks again, Noah. It's great.
Yeah, thanks for having me.
All right. Well, I hope everyone has a great week, and we'll see you in 2 weeks. Take care.